This is One Universe at a Time. I'm Bryan Coker. Graph theory is an interesting idea of connecting dots with lines. It may sound like a simple game, but underneath it is some complex mathematics. On our show today is Dr. Paul Wenger, Assistant Professor of Mathematics at the Rochester Institute of Technology, and he's going to talk to us about the mathematics of graph theory. So when I think of graph theory, I imagine those little pictures of dots and lines that everybody imagines, and the two things that come to mind are kind of like the Seven Bridges problem and the traveling salesman problem. They always seem like nice little games and stuff. Is it just dots and lines?
It seems to me that you actually know more about graph theory than you say what people usually imagine. The fact that you know it's dots and lines means you're already sort of ahead in the game. Usually when I say I'm a graph theorist, people think of y equals x and
graph paper.
Graph paper and the graphs that they drew back in middle school, and they think I do some theory about that. So when you look at it, graph theory in some sense, you can think of it just being the study of abstract networks. So the things you're actually talking about are really networks, sometimes in disguise, sometimes not. So the Seven Bridges of Königsberg question that you were talking about, for people who might not know, the city is now Kaliningrad. It's in this little piece of Russia that's on the Baltic Sea. It's actually not connected to Russia. You have to leave the country to get back to Moscow from Kaliningrad, as it turns out. But yeah, they have a river and they have some islands, and the islands were connected by bridges, and there were 7 bridges. And back in the day, people were bored, I think, and they were looking for ways to pass the time. So they said, well, is there any way I can leave my house and walk and go over every bridge exactly once and get back home? And they thought the answer was no, but they weren't necessarily sure why. And then Euler showed up and resolved the issue so everybody could move on with their lives, and said, well, no, you can't do it. The reason being some of your islands have an odd number of bridges. So if you go off of that island and then you come back on and then go off by another bridge and come on and go off by another bridge, you're going to get stuck not on your home island anymore, and that's right. Good enough to do it. So then what happens is, that's a really simple problem. You know, it was 7 bridges. There's 4 land masses. It's right. Pretty controlled. But then what Euler actually did was he proved that this notion of there being an odd number of bridges at a single island is the only thing that actually matters. So as long as if you have a network where every one of your I guess land masses is connected to other ones by an even number of bridges, and that happens for all of your land masses, then no matter what, you're going to be able to do one of these tours where you go around and go over every bridge exactly once and get back home. So the idea, and this is where graph theory starts, is you have this property on a really small, relatively simple network, but you can use that to get the intuition to then make universal statements about any network you could possibly come up with. This simple
statement now controls any possible network satisfying that idea.
Yes, exactly. So you have what the graph theorists do is we now worry about networks you've never seen before, networks you've never thought about, networks with far more, we would call them vertices, other people call them nodes, the dots you're talking about. People with far more of those, graphs with far more of those dots than numbers anybody have ever thought about. And we try to, determine sort of universal properties that can happen there.
Right. And not just on a surface like the bridges.
Yeah, right. So the bridges, I mean, that's a particular
three-dimensional space or however they want.
Absolutely. So they can be pretty much as complicated as you want them to be. And the thing I look at is, so you say dots and lines, and I'm talking about this in terms of networks. You have these things that are connected. Land masses are connected by bridges. People on Facebook are connected by whether or not they're friends. Websites are connected by whether or not there's a hyperlink between them.
Is that a better analogy?
What?
The idea that people understand the network or the Facebook and how people are connected. That's really kind of a good analogy.
That is the perfect analogy.
What the graph theory is. It is we're the nodes, we're the dots, and our friends and our connections to our friends are the lines.
Right. That's exactly what it is. Like one of my favorite examples that when I'm talking to sort of not necessarily a professional group of mathematicians, you throw up the map of the London Tube system. And that's something that people have seen, it's on a coffee mug or it's on a poster or a T-shirt. People, mind the gap, and they've seen that sort of big mess of a subway system. And that's a perfect example of a graph, because what actually matters when you go down, you're underground, you're now sort of constrained by where the tube can take you. The only thing that matters is, can I get from my station to your station?
Right.
And can I do that in one shot? Is it a direct link from me to you? Do I have to go through multiple stations, but maybe on the same line, or do I have to transfer? And the only thing that actually matters is the connectivity and the relations in that network of how this station over here connects to that station, connects to that station. And that's the only thing that actually matters. So if you see the map of the tube system, geographically it's only kind of accurate. It's really a cartoon of the city. It doesn't actually display the real physical relationship between the location of those stations, because what actually matters when you're underground is how do you get using this sort of restricted connectivity from one station to the other.
It sounds like that would be in a lot of different things, and what comes to mind are airplane networks. The idea that you get onto a plane, you go to some other city, and depending on how many connections you have, that's how many layovers you got or whatever.
Exactly. I mean, I talk about this with students in my classes where, you know, I can go to Orbitz and say I want to fly from Rochester to Abu Dhabi. That's not a direct flight, and Orbitz doesn't really care, but they're taking a path through a network. And you're exactly right that you have certain airports are connected by direct links. Those are your direct flights. So that's another, you know, perfect example. So really, you're talking about networks. And what I think is interesting, and this is where the mathematics comes in, you sort of look around and you start to notice there's networks everywhere, right? Especially now with the rise of social networks and the internet. We've got all these networks. We've got transportation networks. There are tons of problems you can cast as networks. And then what happens is the graph theorist, the mathematician, comes along and says, well, maybe we should just understand networks. Not necessarily motivated purely by a specific example, but I want to actually understand the mathematical structures, right? And this is how we ended up with calculus. If you think about it, you know, Newton figured out physics. He was really, you know, he wanted to know why planets were moving the way they were moving and how gravity worked. And he, you know, developed his, you know, calculus to be able to compute these things. And then what happens is the mathematicians come along and they say, why does that stuff work the way it does? Are we really sure that it works the way he said it did? And then now you have all these fields of calculus, the way we teach it now, is much more motivated mathematically. You know, we tie back into physics. We always use physics examples, but we're studying it more from the point of view that functions have proven to be useful to humanity. We should make sure we actually understand how they work. And that's what the graph theorists are doing with networks.
That's very different. It reminds me of the whole thing with physics that, you know, we always cheat a little bit on the mathematics because we go, well, it won't be physical if we do that, so let's go off and do this. And then the mathematicians come up and clean up.
Oh, yeah, we worry about the details. And I was talking with students just today, and someone said something, well, it makes sense, or it's intuitive that works. And I said, oh, you got to be careful with those words. Because the minute you say something's intuitive, me as a mathematician, I am trained to figure out why it's not intuitive, or I'm trained to figure out the really pathological example that breaks your intuition. And we have a host of them, but there are these books that are titled Counterexamples in Topology, where it's just people sat around and thought up crazy things that mess with your intuition. A lot of times we have to suspend reality. Physicists don't do that nearly as much as mathematicians do, I think.
Sometimes it comes back to bite us, you know, because we're stuck in Euclidean geometry and we think, oh, look, the mathematicians are going off and pretending non-Euclidean geometry. That's fun. You're adorable. And then we come back and go, oh, wait a minute. Space isn't flat. Hey, math guy, can we have your stuff?
Right, and that's one of the hopes of the pure mathematician, is that someday the world will catch up and will need what I'm doing.
Finally, I'm useful.
Yeah, well, not finally I'm useful, but finally I'm useful. I have a cartoon on the wall outside my office that the last panel says all math is applied eventually. I'm on the pure mathematics side, and I dabble in application from time to time, but left to my own devices, I do pure mathematics.
You know, graph theory in some sense seems like a game. If you're just going, you know, well, how many times do you have to cross a bridge to cross all 7? And somebody's going, just cross the bridges. How hard can it be? You know, but the mathematician sits there and goes, no, but I want to solve this problem.
So there are a couple things also, because you mentioned the traveling salesman problem, where the question, right, is you have a bunch of cities you have to visit. You want to go to each city exactly once and get back home. So the difference between the traveling salesman and the bridges problem is, with the bridges, you want to go over every bridge exactly once. With the traveling salesman, you want to go through every city once. And the goal there is to minimize the amount of traveling you have to do.
Right.
And the catch is, right, you know, it sounds like a simple problem, you know, with 10 cities, this shouldn't be so hard to do, but it actually is incredibly difficult to get the right answer, because the complexity of these problems grow in a sneaky fast sort of way. So that's another reason why the mathematicians get enticed, is because you'll see a puzzle or a small problem that doesn't sound so dangerous, and then you poke at it a little bit and you realize just how troubling it is or how difficult it's going to be.
It seems to me like what mathematics typically is.
Yeah. And
easy problem everybody walks past, and then the mathematician goes, oh, wait a minute. Oh, dear.
Yes. And graph theory in particular, something that's great about it is it's really a field that's driven by problems, by which I mean people ask an interesting question or a question that we think is interesting. Like these, can I walk across these 7 bridges in Königsberg and get back to my house? Or, you have these little problems that then motivate the research. It's a little more motivated by problems than, say, by theory. You'll hit well-established, very old classical fields in mathematics like analysis or algebra, where people are studying theory and they're 85 miles deep down the tunnel, digging away and trying to understand something that's, again, very theoretical and very much driven.
Find a diamond out of the
Yeah,
theorems.
exactly. Whereas a graph theorist, we have shiny object syndrome, where it's like, here's an interesting question, and everyone's like, oh, let's go work on that. And it makes it very interesting. If somebody asks an interesting question at dinner at a conference, it gets very quiet. And suddenly everybody's thinking about it, and a lot of scratching of chins. And there was a particularly famous mathematician, Paul Erdős, who kind of was certainly involved in the sort of birth of modern graph theory or modern combinatorics. And he was basically itinerant, effectively homeless. He had a briefcase, and he would just show up at your house unannounced and would knock on your door and say, my mind is open, which meant he was there and he was ready to work. And he was just this incredible talent for posing deep but seemingly simple problems. And there's still Erdős problems that are open. Several of them many of them have cash prizes. So if you're able to solve one of them, you'll get $50.
Right.
But it's like the best $50 you'll ever get.
You'll frame that.
Yes, you'll frame it, exactly. And but he and his attitude, I think, sort of had a real impact on the way our culture in graph theory works, and that it's very much motivated by problems. It's highly collaborative. You basically say, you call someone up and you say, hey, let's do some math together. Here's a problem that's bothering me right now. And you just start banging your heads together and see if you can come up with something. So that's, from the culture side, that's kind of what happens.
This is One Universe at a Time. I'm Bryan Koberlein. We're talking with Paul Wenger about the mathematics behind graph theory. You're a professional mathematician and you work in graph theory. What is your specific area?
So I work in a field that we would call extremal graph theory. People like to make fun of it and say, oh, you're doing, that means you're doing graph theory with a helmet on, or you're doing graph theory on the side of a cliff. It's like, no, that's not exactly what we're talking about. So basically what happens is a really simple example would be, okay, so we've got some sort of a network. We've got people who have signed up for some social network, and they start sort of turning on their friendships. So you see these links between people start to show up. And a question might be, a really simple question, how many people have to be friends before I see that there's a triangle? There are 3 people who are all friends with each other. Now, in an actual social network, this is going to happen very quickly, because 3 people who all know each other are going to, sign up together, and there's your triangle.
People. We're done.
Yeah, exactly. But what will happen is, so now removing it from reality, going to your pure math sort of standpoint, it's like, okay, I get to put these edges between these vertices, so these lines between the dots, the friendships between the friends, in whatever way I want to do it. And I'm going to see if I can just shove as many of these friendships in as possible before I get a triangle. And that's your basic sort of extremal graph theory problem. We've given some sort of a property. I want to make sure there are no triangles in this network, and then we look at some sort of an extremal property. What's the maximum number of edges I can put into it? So you're playing sort of a little local structure, no triangles. Right. That's a very local thing, and trying to understand the global impact of that restriction.
Right. So make one rule and see the implications of those rules within a specific network.
Right, and in particular, usually there's something else that you're trying to push out to some sort of maximum or minimum value. So here, where our rule is no triangles, and then we're trying to maximize how many edges can you possibly stick into that network or that graph. Another thing you could do is you can sort of look at it as how quickly could you paint yourself into a corner. And this is what I tend to work on actually quite a bit, where, okay, I want no triangle still, but what I want to do is sort of do the worst possible job of sticking edges in so that I stick in very few edges, but the next edge I put in, no matter where it is going to cause there to be a triangle suddenly. So it's really this: how quickly can you work yourself into a corner that you can't escape?
Right.
And that's where I tend to do a fair amount of my work, and we have various things we look for, and different settings that we do it in. But broadly speaking, those are sort of an example of the ideas that we.
What does this tell you about graphs?
So what becomes really interesting for us is when you start to get bizarre behavior. That's what makes us excited. And this kind of goes back to what we were talking about, where you have a seemingly innocuous problem that suddenly turns out to be this real mess. So what we like to see is sort of these connections between different problems. So in particular, we have these problems that we've thought about, and what's interesting for us is if you might expect a certain order of growth. So what I mean by that is, let's assume that for the rest of this afternoon, for the rest of this conversation, we always have n vertices in our graph. So there's n of those little dots. That's n people in your network. So the maximum number of friendships you can have, if you've got n people, is going to be about n squared divided by 2. So basically what happens is you pick the first person in the friendship and you pick the second person in the friendship. That's n times n minus 1, which for me is n squared is good enough. And then you divide by 2 because you might have picked them in either one of your orders.
Right. So 10 people, you'd have 50 possible connections. Yeah,
well, so wait a minute. 10 times 9, 45.
45.
45.
Okay,
so because you can't be friends with yourself.
Got it.
That's the rule, right? And so this is the funny thing. You talk to a mathematician or you talk to someone thinking this way, and you say, okay, what's 10 squared? Well, it's 100. And I say, what's 10 squared over 2? Well, it's 50, right?
Right.
For me, 45 is good enough, right? There's some small error that I don't care about.
And you call yourself a mathematician.
Yeah, right? So this is the thing. What you have to do when you become more advanced, right? This happens in physics too, right?
I love it.
You get better at making the right mistakes because the mistakes you don't really care about, right? So those are error terms.
For an easy if you're a simple mathematics, then 100 divided by 2 is 50.
Yes.
But that's never going to get you tenure. 100 divided by 2 has to be 45.
Yeah, you have to be able to say 45 is good enough. 45 is n squared. And these are funny conversations you get to have with students where you can say, is a billion a big number? And the answer is no. A billion's a billion. We could count there. A trillion, we could count there. It would take a while, but we'll finish the job. So you have to think about these sort of limiting behaviors. But so back to the actual question, like the things that we find interesting. So some of these parameters that we talk about, they behave like n squared, right? By which I mean you're going to get lots and lots and lots of all your possible edges. And n squared, so that's something that we would call dense, because what happens is you've got a positive fraction of all your possible edges. So that means it's dense. On the other extreme, or in another way, you could have a linear number of edges. So instead of growing like n squared, it grows like n.
Right.
So what happens is that would be a graph that we would call sparse, right? So there's very few edges.
Every person only has one friend.
Yeah, or if everybody has only 7 friends, you don't have many friendships, right? And you get this sort of interesting interplay between what's happening when you have the very dense graphs versus the very sparse graphs. And what's exciting for us is when you find a problem, and you say, well, okay, so what happens if I put in, into this problem, well, let's think about the triangle. And you say, that's heading off towards n squared. Then you put in something else and it heads off towards n. And there are other little graphs you could put in that head off towards constant numbers. Like no matter what n is, the answer is 12. So it's that different behavior, this sort of this parameter can have multiple different behaviors sort of depending on the inputs, and that's the sort of thing we care about.
Okay.
And what you then start asking is, okay, so wait a minute, I know I can get these different types of outputs. Why do I get the different types of outputs? Where do they come from? Can
you start classifying the type of rules that give you a constant or n squared or n?
Yeah, so what we had was with that question of shove in as many edges as possible, those are basically always up in the n squared part of the game. If you're painting yourself into a corner as quickly as possible, those are down in the linear part. And we were working on a problem a couple years ago that we thought, okay, yeah, this will be linear. This is one of those linear type problems. And we started getting behavior across the entire spectrum. And it was like, that was very unexpected, and we're not really sure what's happening right now, and up is down and down is up, and things felt backwards. And that's the sort of thing that's very exciting. And then you go show your friends. You're like, look at this weird thing I found. It does all sorts of strange stuff. And they say, wow, that's really weird. Let's think about it. So
it sounds like a lot of your research, what excites you the most is not solving the problem, which can be nice, but it's the unsolved problem.
Oh yeah, right. You're always moving on. You're always moving on to the next thing. A person I've done a lot of work with, as a professor, right, we're always trying to write papers, right? You got to write papers. That's the tick mark.
They have to grow by n squared, I think, right?
Yeah, something like that. And I remember, so I was relatively young, and we wrote a paper, and I was really excited. And he said, "You get 24 hours. You get 24 hours to be happy. After that, you're complacent." And I was like, "Oh, that's really pessimistic," but it's really true, because it's like, okay, we solved that. Let's move on to the next thing that we don't understand.
Right. Always
trying to push forward and come up with new arguments, and that's absolutely
This seems to be a commonality between math and science, and
sure.
we get more excited about the questions than we do about the answers.
Yeah. Like every so often you get excited, about an answer. It's like, wow, I didn't see that answer coming, and that was exciting, but usually by the time you find the answer, you're like, why didn't I think of that the first day and move on with life? Because when you look back, it was easy, because you knew, looking back in retrospect, it's like we were so close so many times. Why did we waste the extra 6 months before we realized you could just answer the question real quick?
Right.
But yeah, so the open questions, right? Those are the exciting things to have. A compelling open question is like, I don't know, it's worth its weight in gold.
You're listening to One Universe at a Time. I'm Bryan Koberlein. We're talking with Dr. Paul Wenger about the mathematics of graph theory. You mentioned Paul Erdős?
Erdős.
Yeah. Okay. I know a lot of mathematicians love their Erdős number. They love, it's the smaller it is, the better they like it. And it reminds me of the Kevin Bacon number, how close you are to Kevin Bacon in your movies.
Right.
So this would be graph theory, right?
Yes. Yeah, it very much is. So it's funny because it's graph theory in a couple different ways. First of all, there's a network floating around in the background, so that's graph theory. And the Erdős number is a graph theory thing because he was, at least half a graph theorist. Primarily he was a graph theorist and a number theorist. So, so the Erdős number, right? So if you wrote a paper with Erdős, your Erdős number is 1, and he wrote over 1,000 papers. He was incredibly prolific. I think he was the second most prolific mathematician in history by pages of output. I think behind Euler, I believe it is. And so if you wrote a paper with him, your Erdős number is 1. And now if I have written a paper with someone who wrote a paper with Paul Erdős, my Erdős number is 2. And it goes out like that, sort of as far as you have to go. So my Erdős number actually is 2, which is about as good as I was going to do, because unfortunately he passed away before I was an active mathematician.
The numbers only get bigger after this.
The numbers only get bigger, although I did see a talk where there's someone who has a posthumous Erdős number of 1. So he was, this mathematician, a younger mathematician, was working with an older mathematician who I believe it was Szekélyi is the guy's name, and he was one of Erdős's most common collaborators. And Szekélyi was like, this sounds like something that Paul and I worked on. Let me go look in my files. And he went into his files and pulled out a correspondence, like a series of letters. And it's like, wow, it is. We had thought about this, and he said, well, do you mind if we add Paul Erdős onto the paper? And the young mathematician was, absolutely not. So he's like, I think he might be the last person. I wish I could remember who it was, but I think he's the last person to get an Erdős number of 1. But at this point, I think it's over. 2 is as good as you're going to do. So we all have our Erdős number, and it's sort of funny because it seems to me like the farther a person is away from being a graph theorist, the more excited they are about their Erdős number. Because at this point, if you're at a graph theory conference, everybody's a 1 or a 2. You're either old enough that you worked with Erdős, or the first paper you ever wrote probably got you an Erdős number of 2. So it is funny to see. I've done some work here at RIT with some people over in imaging science, and they had this moment of like, my Erdős number is now 3. It's like, yes, you are. Congratulations.
Yes, you are. Congratulations.
So it is a lot of fun, and right. So it does tie up exactly with that sort of 6 degrees of Kevin Bacon idea. People co-starring in movies, and then the fun thing is there's the Erdős-Bacon number, which is where you take your Erdős number and you add your Bacon number. So whatever the actress is Winnie Cooper. I don't know the name of the actress, but from the Wonder Years. Winnie Cooper has an Erdős-Bacon number because she has a PhD in neuroscience or something, and her stuff connects back. And also Natalie Portman has a relatively low one, and there are some mathematicians that have low ones as well.
I think Brian Greene, I think, has a Erdish of 3.
Okay.
Because he appeared in a movie with Kevin Bacon, and he has an Erdish number of 2.
Sure. I have a very, very, very specious claim to an Erdish-Bacon number, I think, of 4. Because if you go watch, there's the movie Rudy, which is about like a Notre Dame football player. So that was, the football scenes were filmed during the halftime of the 1992 Boston College Notre Dame football game. And I am in the stadium. So like when there's a big panning stadium shot, I am in there. As a kid. So if we allow that, I have an Erdish-Bacon number of like 4 or something. So
okay.
But yeah, it's sort of cool because this is one of those interesting things when you think about social networks and how they work. We were talking before about dense graphs and sparse graphs. And social networks are sparse. We don't know many people, right? There's 7 billion people on Earth, and how many of them do you actually know? Like, how many people do you actually know on Facebook? I don't know. 50, 100,
50, 100,
yeah,
something like
yeah.
that,
You know, you don't know, you basically don't know anybody,
right?
When you get down to it. But one of the interesting things about these networks is you have these sort of hubs that tie everything together. So there's this notion of, even though I only know 100 or 200 people, if we had full knowledge of this network, I could get from me to anyone else in 6 or 7 steps. The idea that one of the terms that's used is there's expansion in the graph, meaning it's very easy to grow out from where you are in relatively few steps and capture everybody.
Right.
So it's really interesting to have this sort of behavior happen, even though there really aren't that many people who are friends in the world, out of all the possibilities. 7 billion squared is a big number, and there just aren't that many friendships around.
Right, right.
Yeah.
Reminds me of, other things where, people talk about in genetics, for example, that after a certain number of generations, you're either related to everyone or no one.
Sure, sure, I believe that.
That either your genes have passed on and they're amongst everybody, or they're amongst no one, because the number of people that we have versus the number that you connect to grows differently. Yeah,
exactly. And this shows up again sort of in other settings, right? The sort of the original PageRank algorithms that Google was using relied on this, because what they wanted to know was, where are the positions that are sort of most central to the internet? And the way they modeled this was, imagine you had a random person clicking just on hyperlinks. A website would load and they'll click on a hyperlink and they'll go to another one. Where's that random clicker going to end up on average? And what's going to happen is they're going to keep coming back to these hubs. And that's how they started ranking web pages, by what's the probability you were just going to get there. Because they could use that as sort of a proxy. If a lot of websites link to my website, apparently my website's important. And that's sort of the premise. And how do you actually detect that in a network? There are pictures of what they call the web graph online, which is, here are all the websites, and here's how they're connected. And as a picture, it just makes no sense. You can't parse it. There's too much stuff. You really can't tell what's going on.
Right.
So to actually be able to look at this information and to be able to say, this is the place that's in the middle, or this is a website of particular importance, that's an interesting problem to try to tackle.
Right, kind of like what XKCD, I think, did a comic of the lands of the internet. Facebook is huge.
Yes.
The New York Times is small in comparison.
Yes, absolutely, absolutely. But yeah, it's sort of an interesting question of how can a graph tell you which vertices are important? And this is the stuff that actually makes, so Paul Erdish is important in the co-author graph of mathematicians, and Kevin Bacon is apparently very important in the co-star graph of Hollywood stars.
Well, I know, like with the Kevin Bacon number, one of the things they said that was critical was he acts in a lot of movies with a lot of ensembles.
Yes.
So he makes a lot of connections with a lot of actors early on. Erdish does the same thing.
Right.
In physics, we might want an Einstein number, but Einstein didn't work with a lot of people.
Yeah.
So it would be really hard to have that kind of social network in that sense.
Yeah, so what you end up with are these sort of hubs who, even though there aren't many edges in the graph as a whole, that one person has a disproportionate number, right? So we had this idea of, we could be sparse if everybody has one friend, right? That's not a lot of friendships. But if everybody's friends with the same person, you don't have many friendships, but suddenly everybody's just 2 steps away from each other because we all know that same really popular person, right? So it's interesting. And these are the sort of different structures we can be talking about, where you can have sort of this global sparseness. There aren't a lot of edges, but there's somehow concentration in a particular spot that leads to actually a, in some sense, very tightly connected network.
So I know a lot of these, I mean, it sounds very game-like in the sense that you're just kind of playing around with ideas and stuff, but the applications are really deeply serious in many ways. I mean, if you're looking at Facebook trying to optimize how to keep people connected onto their network is a graph problem. Trying to optimize how many flights you have to carry everybody across the country or the world, that's a graph problem. Google connecting the internet is a graph problem. It sounds like you're kind of like on the cutting edge of information theory in some sense.
Sure, I hope so. I mean, that would be great. And the thing is, there are a lot of places where you have networks where we might not realize there are. Because sort of what happens, a lot of, say, population statistics, right? So a lot of people do a problem where you have a bacteria colony and you say, oh, they have some sort of a proportional reproduction rate and you get this exponential growth of your bacteria colony. And that's great, but that's an approximation because you can't have a fraction of a bacteria. You either have one or you don't. So one thing that's happening with the growth of computing power is that the world is becoming more discrete. Things that we used to have to smooth out so we could actually think about
kids.
them. Exactly, 2.5 kids. You're in a lot of trouble if you actually have 2.5 kids in the back of your car. You'll get pulled over and you're going to jail. So there. It's true. It's true.
About that half kid, sir.
Yeah. I'm gonna have to ask about that. So things that we used to have to smooth out, we don't have to smooth out as much anymore. And a place that we see this just here with people that we're working with who work in imaging, if they're trying to process a picture, they used to do statistics, and what's happening though is the pixels are getting finer and finer and finer. You're getting higher and higher resolution. And what that means is it's much more likely that two pixels that are next to each other are actually seeing very different things. Because you're more likely to have a pixel that sees the roof of a car, and then the pixel next to it sees the parking lot. And those are very different, and they're not mixed the way they used to be mixed. So suddenly the statistical models that were being used maybe aren't as applicable as they used to be because the pictures are getting better. So some people here are starting to model those with graphs. The idea being if I have two pixels that actually look alike, they have the same sort of signature, I'm going to treat them as vertices that are then connected because they're close by. So now your picture that you're trying to analyze is now a graph, and you're trying to analyze a graph instead. And there are some ways that can be more powerful than doing the statistical methods, or it's maybe a better reflection of what's actually happening. Because stuff is getting
transformation gives you more power because now you've got all the power of graph theory behind you.
Exactly. The flip side of it is you run into sort of hairy computational problems that can be an issue. But so that's something that's interesting. I remember I had a friend in grad school, and this was like the first time someone came at me with sort of an applied problem, and I did not answer it well. He said, "How do you know if a graph's connected? How is it all? How do you know if it's all in one piece?" And what he was asking was he was looking at a species. And he had a network set up on this species of sort of individual beings. And the question was, when do so many of the connections break that you now have two species instead of one? He was doing some evolutionary or some math behind evolution theory.
Right.
And from my point of view, as like a real novice graph theorist, it's like, well, you're either told at the beginning of the homework problem or you're not. It's either let G be a connected graph or let it not be a connected graph. But as it turns out, and it also sounds like at the beginning, it's like, that's kind of a silly question. You sort of look at it and you pick it up and you shake it and it either falls apart or it doesn't.
Right.
But as these networks get huge, it can be incredibly difficult. Even you can't look at a picture because I could jumble it all up and you can't tell if it's in two pieces or one piece or 1,000 pieces. So you have these sort of interesting problems that are arising. Again, as the world gets more discrete and as we pick up this computing power, the graphs start popping up and suddenly it helps to know about them.
Right. And with big data and the ability to analyze this level of data, you've got this kind of pinpoint precision and the power to analyze it.
Some of the power to analyze it, not necessarily as much power as you want to analyze it. We always want more power.
Conspiracy theory you believe, right?
Yeah, exactly. But it is sort of funny to, every so often, and again, I'm a pure mathematician as my background. Every so often I'll see an applied thing and someone will say something with a graph, and I'll be able to say, just because I'm familiar with graphs, I don't know what their particular domain problem is, but I'm familiar with graphs, and they start using the graphs, and I can look at it and be like, I'm not sure that's working exactly right, or you might be able to do something here. Just because I understand the mathematical structure in the background, I can try to maybe contribute to their very real, very applied real world problem.
Right, and that's one of the powers of the mathematics of graph theory, is that once you've connected it to a graph, then it becomes purely theoretical.
Yes.
Then that's your territory.
Exactly. And it is funny because there's someone said it better, and I'm going to do a bad job of quoting it, but people talk about the unreasonable usefulness of mathematics or something. Like, there's no reason why this should work as well as it does. But just time and again, it keeps working, and as more application fields sort of intersect with more bizarre parts of mathematics, it's sort of fun to watch as what seems to be very pure stuff suddenly becomes very applicable and very useful.
You've been listening to One Universe at a Time. We've been talking with Dr. Paul Wenger, Assistant Professor of Mathematics at the Rochester Institute of Technology, about the mathematics of graph theory. Our program is produced by Mark Gillespie at the Rochester Institute of Technology with support from the RIT College of Science. Thanks for listening to One Universe at a Time.